Welcome to the new era of video creation with Bayozi 8. Today, we will discuss about e-commerce platform with millions of users and products.
Question. You are tasked with designing and deploying an AI-based recommendation system for an e-commerce platform with millions of users and products. How would you approach this problem, focusing on model design, optimization, scalability, and evaluation? The primary objective is to design a recommendation system that tailors product suggestions to users based on their historical actions and preferences. As we are dealing with millions of users and products, scalability is crucial. High throughput is necessary to ensure that the system can handle thousands to millions of requests per second, and low latency inference is required to provide near-instant recommendations in a dynamic environment. The recommendation engine will rely on transaction data, such as past purchases, user behavior data, clicks, searches, or views, and product metadata, categories, prices, descriptions. These data sources must be processed and integrated effectively to build a highly accurate and scalable recommendation system that serves diverse user needs and product preferences. Data is fundamental to building a recommendation system. We must first collect data from various sources, including user activity logs, e.g., clicks and views, purchase history, and product metadata, e.g., categories, product tags. This raw data often requires substantial preprocessing. Missing values must be imputed, categorical data normalized, and noise filtered out. After cleaning, we can aggregate the data to create features that represent the user's behavior, such as frequency of interaction or recency of purchase. One of the main challenges is dealing with sparse data. For instance, the interactions between users and products. In these cases, techniques such as embedding layers can be used to represent sparse features like product IDs or user IDs in dense vectors, making it easier for the model to learn and generalize patterns. For recommendation systems, collaborative filtering is a popular approach where the system makes predictions based on historical interactions. One of the most common techniques used here is matrix factorization, such as SVD or ALS. In matrix factorization, a user-item interaction matrix is decomposed into latent factors that represent users and products. These latent factors capture hidden preferences or characteristics that help the model predict interactions. However, a well-known limitation is the cold start problem. New users or products have limited interactions, making it challenging to generate meaningful recommendations. This can be mitigated by incorporating content-based filtering, where product metadata such as categories or descriptions is used to recommend new items or users who have limited past behavior. In addition to traditional collaborative filtering techniques, deep learning models have been increasingly successful in recommendation systems. A well-known deep learning-based method is neural collaborative filtering, NCF. This technique uses embedding layers to convert user and item IDs into low-dimensional vectors. These vectors are then combined through an MLP, multi-layer perceptron, which allows the model to learn nonlinear interactions between users and products. This method can capture more complex patterns in user preferences, especially in large-scale systems where traditional matrix factorization methods might struggle. NCF often outperforms classical models by detecting intricate relationships between the user and item data that simpler models may miss. For more robust recommendations, we can combine collaborative filtering with content-based filtering in a hybrid model. Collaborative filtering uses interactions between users and products, while content-based filtering leverages product metadata or user attributes. This hybrid approach can deliver more accurate recommendations by providing both implicit and explicit signals. Additionally, combining methods like matrix factorization with deep learning models can further improve performance, as deep models capture nonlinear patterns that matrix factorization may miss. Moreover, incorporating multimodal data such as product descriptions, text, images, and other metadata can create more contextually relevant recommendations that go beyond what the user has interacted with, thereby improving recommendation quality and user satisfaction. Scalability is a key challenge, especially with millions of users and products. For model training, we would likely use batch learning, where large volumes of historical data are processed periodically. However, For maintaining up-to-date recommendations, we also need online learning capabilities so that the model can continuously adapt to fresh data and trends. For distributed training, we can leverage multi-GPU setups or even distributed systems, e.g. Horovod, to scale training to large data sets. At inference time, we must ensure low latency predictions, which can be achieved by model quantization, reducing model size, and knowledge distillation, transferring knowledge from a large model to a smaller, faster one. In production, a microservices architecture is ideal for scaling, as it enables easy deployment and maintenance of real-time recommendation APIs, ensuring fast and responsive user interactions. To evaluate the effectiveness of a recommendation system, a combination of evaluation metrics is needed. Precision and recall are the standard metrics to assess how well the system is recommending relevant items. Precision looks at the proportion of recommended items that are relevant, while recall measures how many relevant items are actually recommended. Mean reciprocal rank, MRR, is another important metric for evaluating the ranking of items in the recommendation list, how quickly the first relevant item appears. RMSE, root mean squared error, is often used in collaborative filtering to evaluate the accuracy of predicted ratings. Lastly, diversity and novelty are important for ensuring the system doesn't recommend similar products repeatedly, thereby enhancing user engagement by offering a wider range of products. One challenge in recommendation systems is data imbalance, particularly when dealing with implicit feedback, e.g., clicks, views, where many interactions are unobserved or negative. One solution is negative sampling, where we assume that items the user hasn't interacted with are negative examples. Additionally, class weighting can help by giving more importance to rare items or less popular interactions. This ensures that the model doesn't overly favor popular items. Regularization techniques such as L2 regularization can also help avoid overfitting, particularly when using collaborative filtering methods that might focus too much on frequently interacted items, neglecting the long tail of less popular items. Once the recommendation system is deployed, continuous evaluation becomes vital. A/B testing is a powerful method for comparing the performance of different models or configurations in real time. By splitting the user base into treatment and control groups, we can evaluate which recommendation model delivers better results in terms of user engagement or sales. Continuous evaluation of model performance ensures that issues such as model drift, where the model's accuracy decreases over time due to changes in user behavior, are quickly identified. Model versioning helps maintain control over different model updates, and incremental updates allow the model to adapt to shifting patterns in user behavior or new product offerings. Privacy and ethical considerations are essential when designing AI systems, especially for e-commerce applications where user data is highly sensitive. Data privacy is paramount, and the system must comply with privacy regulations like GDPR. Bias mitigation is another critical area. The system should be regularly audited for bias in its recommendations, ensuring that it doesn't unfairly favor certain products or user groups. Transparency is essential in building trust and providing explainability on how recommendations are made, whether they are based on historical behavior, user preferences, or product popularity, is vital. Finally, ethical considerations include ensuring that the recommendation system doesn't promote harmful or discriminatory content, fostering a fair and responsible user experience.